Okay, so we will talk about sorting problem. So, the problem of sorting. So, basically we have an input of size n, say we have an array a1, a2, an, and the output will be a rearrangement or a permutation of this array ain such that a1 ai2 less than ain. So, this is a rearrangement of the number in a sorted way. Now, example is, suppose we have given this array say 6, 7, 1, 2, 9, 5, 4. Suppose this is our input. Now, we want to sort it. So, the output will be 1, 2, 4, 5, 6, 7, 9 sorted. So, we will look at some way how we can do this. So, first algorithm we will be looking at what is called insertion sort. So, the input is an array of size n. So, we have a for loop for I is equal to 2 to, or we can say j is equal to 2 to n. We put this in key value and we take I is equal to j minus 1, and we have a while loop while I is greater than 0 and ai is greater than key value, then we have to ai and this, and then we reduce I by I minus 1, and then so this is 5, 6, 7. So, here now we put ai plus 1 is equal to key. So, this is what is called pseudocode. So, pseudocode means it is not a very much English description what we are doing, but it is a language. I mean, it is in for loop we are, but it is also not a some specific syntax of the language like C language. But if we can give this to some programmer, he or she can easily implement in that particular language. So, that is called pseudocode. Okay. Now, let us try to understand this. So, what is the loop invariant? What we want? Loop invariant is, so our j is pointing somewhere here. So, this is our, at some point of time, this is our key value, which is basically aj. Now, initialized by 2. Now, it is trying to find out its position like this. So, by shifting this like this. So, finally, if we got the position, we will put this value over here, and every time we are shifting this way like this. Okay. So, we can take an example to execute this. Suppose we have these numbers 8, 2, 4, 9, 3, 6, and we want to sort this using the insertion sort. So, we are starting with j is equal to this. So, this is our key value, and then our I is basically j minus 1, I we are starting with this. Now, as long as I is greater than 0, I is greater than 0 and ai is greater than key. So, if ai is less than key, then we do not need to do anything, but if ai is greater than key, then we need to find out the location for this ai by shifting this. So, what we do? We will shift 8 here and we reduce I by 1. So, I by 1 it will be 0. So, we stop there. So, we will put this key here and now j is pointing here. This is by that for loop. So, again this is our key value and we what we do? We just look into this. So, this is our, now we put I is equal to this. Now, we look at here. So, this is I is, I mean key is ai is greater than this. So, we will shift, we have to shift here and then I is I minus 1. So, that is this, that is not 0, but now the ai value is less than key. So, we will not go for this loop. So, we will just put a of I plus 1 is equal to key. So, 4 will be here like this. So, now j is pointing here. So, now this is our key. So, we compare this with the previous value. So, every time if we observe this part is already sorted. Now, we need to find out the position for this guy and this is greater than. So, cool, no need to do anything. So, we will increase j by 1. So, j is now pointing here. Now, we compare this. So, we compare, so this is our I now. So, we compare this is less. So, we shift this here, we shift here, we shift here and finally, we put 3 here. So, 3 has to come long way to here and now 6 is the new I, this is the new key. So, again we do the same thing, 9 will come here, 8 will come here and 6 will be here. That is it, j is gone. So, this is the execution of this code. Okay. Now, what is the runtime of this algorithm or runtime of this piece of code? So, well, runtime will depend on few things like what is the, I mean, when we do not need to do many comparison here. If the input is sorted, if the input is already sorted, we just need to compare with the previous one, that is it. But if the input is reverse sorted, that means everybody has to come a long way to the beginning. So, the runtime will depend on the input, the pattern of the input, and also it will depend on the size of the input. Suppose we need to sort 10 element and we need to sort 100 element, obviously 10 element will take less time than 100 element. So, we can parameterize this runtime by the input size. Suppose Tn is the runtime for n element. So, so this is the parameterization we are doing. So, n is runtime is Tn, where n is the size of the input. Okay. So, we will do 3 types of analysis. First one is worst case. So, that means Tn is the worst case, means we have to see the maximum time it is requiring for any input. Say for the worst case, for insertion sort, if the input is reverse sorted, then it is the worst case, because everybody has to come forward to the beginning. Okay. So, now this is the maximum time required to sort n element for any input Okay. That is sort of guarantee. We can guarantee that this is an upper bound. We can guarantee that our time is this much maximum, whether any input you can give, no matter the input you choose, our algorithm will perform like this. It will not be worse than, it will not be better than which I am claiming. So, that is the usual analysis we will do, because we want the guarantee. This is sort of guarantee. Okay. The second one is average case. Average case means sometimes we will follow some distribution of the input and we will see how this T n is. So, T n is the average runtime or expected. Okay. And the last one is, which is really bogus, base case. Best case means sometimes, like for insertion sort, when is the best case? If the input is already sorted. Okay. So, it is a bogus. I mean, if we design a sorting algorithm and if you give it to somebody to purchase and you tell, okay, this is my sorting algorithm and this is performing very nice for this type of input. So, you are declaring your pattern of the input where your code will perform good. That is the best case, but nobody will believe that. People will try for all other input and see where your code is performing bad. So, that is why we will not prefer to go for this best case. This is sort of cheating. You are cheating by providing the input. For this type of input, my algo is good, but you are hiding that usual case analysis. You have to tell what is the maximum runtime for your code for any input. So, that is the usual analysis we will do. Okay. So, apart from that, suppose we want to do worst case analysis for insertion sort. So, we want to do worst case analysis for insertion sort. So, worst case means input is reverse sorted. We have given an input which is reverse sorted. That is the worst case scenario for the insertion sort. So, then let T n be the runtime, where n is the size of the input. Now, will it depend on any other thing other than this? Any other factor will contribute in this runtime. We have fixed already T n, we are dealing with the worst case. So, any other parameter or any other factor will be affecting this runtime. Yes, it is the speed of the machine, the computer you are running this code. Suppose you are running in a Pentium 1 computer or some old microprocessor 8085, 8086, and you are running this code in a brand new laptop code to processor. So, obviously, code to processor will take lesser time than this. So, it will depend on the speed of the machine. So, runtime also depend on the speed of the computer. Okay. So, suppose I calculate my runtime and it is coming out to be this, say 100 n square plus minus 60 n plus 3. This is my runtime, this many second, and these are the factor, these are the terms are coming from how much time we are spending in the adder, microprocessor, heating time, everything. So, we just calculate those, and this is the exact runtime for my code. And suppose my friend is having another code which is having runtime like this, 2 n cube plus 6 n plus 3. My friend also calculated using the the time spending in the hardware and got this much second. Now, which one is the better? This is my code, this is my friend code. So, if you draw this with respect to n, so one will be like this, another will be like this. Okay. So, so this is, so up to this, so this is my code T1 and this is my friend code T2. So, we will see after certain time up to a certain point my friend's code looks like better, because this constant factor is less, but actually my code is better, it is having order of n square. So, that is why we need to bring a great idea which is called asymptotic notation. So, we want to get rid of this constant term which are basically machine dependent terms. So, if we how we can get rid of, we just ignore the constant term, we can ignore the lower order term and then we ignore the leading coefficient. So, this is basically order of n square and this is order of n cube. So, this is better and this is in the asymptotic sense. We will formally define what do you mean by order, the big theta, but this is the idea. So, we want to get rid of from the machine dependent constant, machine dependent terms. So, that is the reason. So, this should be the better code than this one. Okay. So, let us define what is, so what is big O of big theta of n square. Asymptotic analysis we will do. So, we will ignore the machine independent time, machine independent constant. Suppose our time is say 100 n square minus 10 n plus 3. So, these are the constant coming from the this many seconds say coming from the machine dependency. So, we want to get rid of this constant. So, we want to see the growth of this n as growth of T n as n tending to infinity. So, this is basically we will denote this by order of n square. So, we will ignore the all lower order term, then we ignore the leading coefficient, this will give us the big theta of n square. We formally defined what is big theta. Okay. So, now so big theta of g of n is the set of all function f n such that there exist two positive constant C1 and C2 and f n is bounded by this. So, that means big theta of n square, if g n is n square, is basically set of all function f n such that C1 n square less than equal to f n less than equal to C2 n square. So, now this is the big theta. Now, big O is basically big O of n square, big O is basically the upper bound. If we have only this, then it is called big O. So, big O of n square is set of all functions such that f n is less than equal to some positive constant C n square. Similarly, big omega of n square is the lower bound. If we have only this, then it is called big omega of g of n, if g of n is n square. So, this is basically set of all functions such that f n is greater than equal to some constant n square, positive constant. So, this means we want to look at the growth of this function as n tending to infinity. So, we will not look at the few terms lesser value, we want to see where this T n is going as n tending to infinity. So, that is in asymptotic sense. So, what is the worst case? So, insertion or worst case means the input is reverse sorted. If the input is reverse sorted, then we have a for loop and everybody has to come forward. So, the runtime is basically order of So, this is basically order of n square. Okay. So, this is the worst case. Now, what is the average case? So, in the average case we are assuming that on an average everybody has to come halfway to the beginning, I mean halfway. So, T n will be j to n. So, this is also will be order of n square. This is the average case for insertion sort, but for the average case we need to take the probability distribution of the input and then we need to do the proper expectation of that runtime. But this is in a informal way to say the average case for insertion sort. Now, when is the best case for insertion sort? Best case is the if the input is already sorted, that means we are comparing each element once only. So, it is basically T n is basically then summation of. So, this is a best case for insertion sort. Now, we will look at a sorting algorithm where we will see the average case is better than n square, which is a n log n algorithm, that is merge sort. So, we have an array of size n. So, in the merge sort what we do? So, if n is equal to 1 we return, because only one element. So, one element is already sorted, nothing to do. Otherwise, we go into the middle, n by 2, I mean ceiling we have to put to make it integer, and then we sort this and sort this recursively. Okay. So, this is a recursive call. So, else we recursively sort, we apply the same merge sort on a 1 to n by 2 and a n by 2 plus 1 to n. So, we have basically we have sorted this subarray, this subarray. Now, once we have two sorted array, now we need to merge these to get the whole sorted array. So, we apply here a merge subroutine which will take two sorted array subarray and which will give us the whole sorted array. So, what is the merge subroutine? We have two sorted arrays, say 8, 6, 4, 3, 1 say, and we have another sorted array 12, 9, 12, 7, 5, 2 say. We have two sorted array. Now, we will explain the merge subroutine. So, what we choose? We choose the minimum smallest element of these two sorted arrays. So, smallest element will be the first element. So, we point the smallest element of this two sorted array and we take a auxiliary array of size n to store this. Now, we choose the smallest among, we choose the smallest one among the smallest. So, 1 is the smallest. So, we output 1 and next we point to the next smallest element of that array. Now, we compare again these two smallest and 2 is the smallest. So, we output 2 and we choose the next smallest. So, we compare these two smallest, 3 is the smallest. So, we output 3 and we point to the next smallest. So, we compare these two, 4 is the smallest. So, 4 will be the output and we choose the next smallest. So, we compare these two smallest, 5 is the smallest, 5 will output here and we point to the next smallest. So, now 6 is the smallest, 6. So, 7 and 8. So, 7 is the smallest. So, 8 and 12, 8 is the smallest. So, only one. So, this is 12. So, this is the, and for this we need to have an array of size n to store this. Okay. So, this is the execution of the March subroutine. Now, how much time we are spending here? Suppose we have a roughly n by 2 element. So, we are comparing the each element one time. So, it is basically a linear time algorithm. Okay. But here we need a extra array, that to be noted. Okay. Now, what is the time complexity for merge sort? Suppose Tn will be the time for this. So, how much time we are spending here? It is basically constant time, and how much time we are spending here? So, we are doing two recursive call. We are calling the merge sort here, merge sort here. So, this size is n by 2. So, time will be Tn by 2. This is also Tn by 2, but here we may use the lower ceiling or upper ceiling, but this is equal to 2 T n by 2. So, the total time is Tn is equal to 2 T n by 2 plus theta of n. So, this is what is called recurrence of this code of this merge sort. Now, the question is how we can solve this recurrence. So, one way to see the solution, we can use what is called recursive tree or recurrence tree. Okay, so, this is our recurrence, Tn is equal to 2 T n by 2 plus Cn, that theta n we can just put it at Cn. So, now what we do? So, Tn is basically can be written as Cn Tn by 2 Tn by 2. So, these are the time required to solve these two sub problems, and this is the combined time. Now, again if we assume the same recurrence we will use again. So, this is a problem of size n by 2. Again we are dividing this problem into n by 4 like this. So, this will be Cn by 2 Tn by 4 Tn by 4 Cn by 2 Tn by 4 Tn by 4. So, Tn is basically sum of all these nodes. So, this way we continue. So, Cn by 4 until we reach to a T1. If there is only one element, we stop there, that is the T1. Cn by 4 like this, every branch will stop at T1. Cn by 4, sorry, this is Cn by 4 like this. So, this is Cn by 4 like this, every branch is stopping at T1. Okay. Now, that we have that total time Tn is the sum of this all time. So, this is you can do the level wise sum Cn and so everywhere it is Cn. So, the what is the height of the tree? Height of the tree is log n, because it is a complete binary tree. So, the time is, so the time for merge sort is n log n. So, this is the time complexity for merge sort, and this we are achieving using this recurrence tree. In the next class, we will see some other method to solve the recurrence other than the recursive tree, like master method, and so we will discuss in the next class. Thank you.